Okay, hey everybody. Thank you so much for coming. My name is Mason Newburgh. I'm one of the two co-directors of KSS, the Kimball series. Anthony back there is the other co-director. And a number of the people who kind of made this event possible are spread throughout the room. If you're a member of KSS, please raise your hand. Okay, thanks guys so much for all the work you've done to make this possible. KSS is an organization that works at the intersection of, tech, science, ethics, and geopolitics. Our goal is to bring together audiences of technically minded people or technical backgrounds, as well as policy/social science focused individuals, to really talk about some of the most pressing issues of our current day. So today we have a super exciting event for you. Without further ado, I'll let Harsh, one of our team members, take it away.
All right, thank you so much, Mason. Understanding the early universe hinges on two pillars, the cosmic microwave background and 21 centimeter radio spectroscopy. And so Professor Laura Newburgh has been involved in both of these frontiers, and she's involved in collaborations such as the Simons Observatory, which measures the cosmic microwave background, CHIME and HIRAX, which map the cosmic structure through 21 centimeter signals to study dark energy. And however, these ground-based observational techniques have faced a growing threat from satellite constellations causing optical and radio interference. So remote locations have historically enabled for telescopes to avoid most of this interference. However, that's no longer the case, with a dramatically increasing number of low Earth orbit satellites. So that's going to be a focus for today's conversation. To begin, thank you so much for coming, Ben. Maybe you can talk a little bit about your work and how it has been impacted by the satellites.
Yeah, sure. Yeah, so I'm Professor Laura Newburgh, faculty in the physics department. So I would say there are two examples I'll give. So one is CHIME. This is a radio telescope that we put in Canada. We built it. So we started building a pathfinder for it actually back in 2013, which is so long ago, I don't want to think about it. But put the full instrument together, and it started collecting data in 2018. When we built CHIME, our spectral band, which happens to be 400 to 800 megahertz, was basically clean. There were a few things, a few digital cable bands, et cetera, but for the most part, it was totally clean. Fast forward to today, I think 60% of our band is taken up from RFI, radio frequency interference, from cell phone bands, GPS, satellites, things like that. So we didn't predict this very well, and so our algorithms for removing this radio frequency interference from our data are pretty stupid and not necessarily as effective as we'd like them to be. But it means that there are frequencies in our data that we only observed for 1 year, and now it's gone. We'll never get that data again from our instruments. The next generation of CHIME, which is a bunch of dishes that are going right next to the telescope, the big telescope, we'll have to contend with this and have more real-time RFI removal so that you can remove a lot of the things directly in the data before you integrate it down and analyze it and all that other stuff. So, one of my experiments was just 100% impacted by the fact that Canada auctioned away that band while we were basically starting to observe the sky. The other experiment that I work on, the one in Chile, is in higher frequencies, so 20 to 270 gigahertz, so much higher frequency. For a long time, these were pretty safe from satellite transmissions because that's a high enough frequency that a lot of the instrumentation is complex and you probably wouldn't put it on a satellite. Of course, technology only gets better. And so we got the first notification that Starlink was starting to use a fraction of one of our bands for the Chilean satellite, Chilean experiment, just 4 days ago or something. So nothing's safe anymore, basically. We'll have to contend with that. I think one of the one of the problems is it's difficult to advocate for your RFI band, right? So for the Simons Observatory Science, the Chilean experiments, you know, we may advocate that they never, Starlink and other satellites maybe never actually observe in our main science bands. But even then, the other bands outside of it are still necessary to do our core science, to remove a lot of the contamination and other things that we need to remove in our data to get at our core science. So, you know, it can be difficult to advocate that you need like whole fractions of these bands to please don't use this frequency. So yeah, I mean, you know, it's basically the radio version of sort of dark skies for optical telescopes. So we really need to keep these bands clean, or you won't be able to observe the sky at all anymore.
Is there a signal or some sort of science that you worry the most about losing?
Yeah, I mean, the CHIME science is hardest because those, like, okay, so the 21 centimeter, its native frequency is 1.4 gigahertz. Your Wi-Fi that you use here is 2.8 gigahertz and goes up to 5 gigahertz for 5G. So, like the 21 centimeter band, if you're looking at redshifted 21 centimeters, so light that the universe made a long time ago, the wavelengths of that 21 centimeter, 1.4 gigahertz light has expanded over time. So you're always looking at these like lower frequencies where even FM bands, so ignoring space for a second, FM bands can kill you. This is also exactly where digital cable and cell phone frequencies have ended up. So that science is just like primary target. And that's just because it's easy to build cell towers and instrumentation for these things. So that's, you know, the lowest hanging fruit if you're a communications company. It's already cheap to get the amplifiers and all the components you need for it. So yeah, so that's the worrying one. The space ones, I think, like are more likely to begin targeting the higher frequencies around the CMB science. Cosmic background science, sorry, at way higher frequencies. And because if you're gonna build something and stick it in the sky, like you might as well make it the most, you might as well cram as much technology onto that as you possibly can. So that, I think we'll start seeing those operate at these higher frequencies. You get more bang for your buck, you can cram more data into the higher frequencies than you can at the lower frequencies. So they'll probably quickly start moving into these high frequency bands. Yeah.
Also, I should maybe give it a little bit more context at the start. So we'll have a Q&A up front for around 30 minutes, and then we'll open it up to the audience so you guys can ask some questions at the end, and we'll have a small group discussion to close it off. But yeah. So I just thought of that again. So, but yeah, so obviously there is this inherent tension between the scientific community, which ideally would like a dark and quiet sky, and the commercial and societal drivers, which advocate for an expanding satellite network. And so, is there a sustainable middle ground, and how can you advocate for such?
Yeah, good. Hopefully all of you guys will figure this out. I'm not sure what the middle ground exactly is going to be. So I'll say, and I know we talked about this a little bit, like I'm very sympathetic to, for example, Starlink, right? So it was the only form of communication for people who are going through floods, hurricanes, things that are taking out terrestrial forms of communication. It's your only link to knowing your family is okay, getting resources you need. So I'm my aunt lives in Florida, so she's like, thank God Starlink exists. It's the only reason I could tell you guys I was okay. So, Ukraine, similar. In fact, in our Chilean telescope, the very one that's gonna, have its band slowly eaten away by Starlink, we use Starlink for our secondary form of communication. So we have a fiber link that goes to North America, but it got cut last week and our backup was Starlink. So, I am very sensitive to the fact that, we need communications, and Starlink is providing an incredibly valuable version of it. At the same time, I'm not even sure what the process is for Starlink deciding what frequencies go up. It feels like we only learn about them when we see them in our telescope data, and there's something like, what happened? So, there does seem to be kind of a mismatch of these bands get auctioned away, and you literally, I'm not sure what the input is from the scientific community. For, there's one model that is certainly worked in the native 21 centimeters, so again, that's 1.4 gigahertz. So that band is clear. No one is allowed to build any instrumentation in a band around 1.4 gigahertz, and that's because astronomers are very interested in local neutral hydrogen. And so the entire world decided, fine, you like this one little bit, astronomers get to have it, we'll figure out what to do with the other parts of the spectrum. So there is, and that was done, that was negotiated, but, so there is one working model for at least being able to say, can we have some parts of these bands that might be clean? There's been growing interest, and there was a call for proposals a couple of years ago from the NSF for shared spectrum. So this is basically a building technology that allows both the satellites to exist and the science to exist. So this would basically be a communication between the telescopes and the satellites that says, if you're either pointed the other way or somewhere else or whatever, such that we should be able to see our frequency band should be clean for this 5 microseconds of time or whatever, we get that time, and then you can have some other time, et cetera. So you can negotiate's the wrong word, but you can use the time, scientists can use the time, and the satellite might not be overhead. You may be able to use that to say, we really need this one, 5 microsecond period of time. Can you not be in your signal directly to the telescopes during that? So, so I think that's a technology challenge first. But I think is kind of a recognition from the NSF, the National Science Foundation, that advocating for entire chunks of the band to be clean is probably not going to get us very far, and so we need to think of different ways of figuring out how to share and occupy these bands. So I think something like that, feels like a little bit of a cave-in from the scientific community, but may just have to be what we end up focusing on, so that we at least get some parts of we get something out of this.
So the strategies you suggested require a lot of international collaboration, and how possible do you think that is in the current climate where countries are increasingly isolationist and not collaborative?
Yeah. Okay. Yeah, exactly. I think it's going to be hard. Yeah. So there's a Russian satellite actually that just blasts a signal right into CHIME. So we're probably not supposed to know about it, but we do. Yeah. Certainly the spectrum. Okay. So there are overall governing bodies, both internationally and within each country, to have to work on spectrum management. So I've given talks in front of CORF, the Committee for Radio Frequencies, which is a National Academies committee that talks to the international community, the international governing body of the radio spectrum, communicates with the spectrum managers at both the NSF and NASA. So those are the people who say what frequencies are getting used by the people who get these grants. And then the FCC, which of course is the actual regulating body that auctions away our bands, but determines the spectrum use within the United States. So there is communication and ways of advocating for spectrum use from science, within the U.S. and then also internationally. This probably worked better in previous years than it does now. I don't know what's going to happen as we go forward. But I think many places still think science is important and really open to being able to make sure that parts of the band are still free so that science can happen. You do worry more about, for example, Russia and things where that you just probably have no real communication about it, and as long as it's not impacting their telescopes or whatever, like who cares? But But, I mean, we'll see what happens as we go forward, but there is an established mechanism for being able to govern the spectrum internationally, and at least negotiate these things internationally. Yeah.
Staying on this topic about tension between the commercial side and the scientific community, what do you have to say to commercial actors such as Elon Musk, who maybe suggest that this is a very temporary problem, right? Like eventually we'll have telescopes in space, or we'll have some extreme suggestions have been made to put telescopes on the far side of the moon. Right, so what do you say to these?
Yeah. So I mean, there are some things like actually going into space is a really good thing. So your example of the far side of the moon is one. So there's a radio telescope, again, if it gets launched next year, pending funding. It's planned to be launched next year, I should put it that way. The plan is for it to be on the far side of the moon. That frequency, it's a 21 centimeters. It's also looking for neutral hydrogen. Very, very redshifted. So looking basically all the way back to the very first neutral hydrogen in the universe, from whence the first stars, et cetera, were born. That frequency range is entirely contaminated from the FM band from radio off of Earth. And so you cannot make those measurements on the Earth. Those FM signals are everywhere. There's no clean place anywhere on the surface of the Earth. I should say AM, in fact, AM. So the plan is basically you put it on the far side of the moon, so you shield the telescope from the Earth's FM and AM emission by the literal body of the moon. And so they're going to launch it next year. Yeah, and assuming everything goes as planned, they're going to launch it next year and do a demonstration telescope. So that's in fact, to do that science, that's basically what you have to do. There's no other way around it. Elon Musk has said, that all these problems are temporary because eventually all of the telescopes will be in space, and so clearly he doesn't really understand the problem, which makes sense if you're one of your companies is launching stuff into space. I too would probably feel the same way, but there are telescopes we simply can't put in space. So 30-meter telescopes in the optical are an example. You're not going to launch one of those. The interferometers that we build in radio, across radio astronomy, those we have a really hard time fielding in space. And so, it's not, plus the more stuff you put up there, the more space junk you have, and the more you'll get collisions and problems with your telescopes that you put there in the first place. So, just believing that this can all be solved by putting everything in space is not particularly, not a particularly good solution. It certainly misses core reasons why we do a lot of the science that we do. So one way or the other, we need to figure out how to share this spectrum and share these guys. You had another part of your question that I feel like I forgot, but please answer.
Right, I guess maybe, I maybe I was trying to ask if there is a long-term need for ground-based telescopes if we export all these telescopes to space.
Yeah. I think there are so there are good reasons sometimes to go to space. Things like the frequency range you're interested in, you literally can't see through the atmosphere. X-ray telescopes always have to go in space. Infrared telescopes frequently benefit from being in space, et cetera. So there's a space case for different types of telescopes. Telescopes that you can use from the ground tend to be much bigger, right? So the radio interferometers that we build are kilometers wide, and some of them, like the ones that image, the millimeter ones that image I don't know if you guys ever saw this, a couple of years ago, 5-something years ago, millimeter interferometry was used to image right around a black hole. So you could actually see the edges of those black holes region. That was using basically a telescope the size of the Earth by combining signals from across the face of the Earth. Things like that just aren't, you can't do that from space. And so you know, it's just, there's some science cases that will never work. And those, many of them are some of the core science cases that we want. It's incredibly expensive to put things in space. So if you'll never make it cheaper than, especially for something with really huge telescopes, it will never be cheaper to put something like that in space. And the amount of, you know, a 30-meter telescope is just impossible. We should just not even mention it. Yeah, so there are just many science cases where you will always end up putting something on the face of the earth. You need to figure out how to use that spectrum. And,
So talking about ground-based telescopes, what engineering challenges or what ideas people have to combat this increasing number of satellites, maybe data analysis, or maybe engineering techniques to deal with these experiences?
Yeah. So like I said, so on the technical side, there are things like the shared spectrum concept that may come to fruition. So CHIME, like I said, didn't, my telescope that I work on in Canada, didn't prepare for this future particularly well. And so most of our analysis routines, most of our analysis routines can't do any real-time flagging of this RFI. So to give you a sense of what it usually looks like in the data, like there's RFI that's probably happening very, very, very rapidly. We integrate our data into 10 seconds. And so we just eat all of it. We just integrate all that low-level stuff. And the only stuff we cut then is when you have a big flare of it that manages to look like something really bright. And then you cut that frequency in that time period. That's that was fine when we didn't have a lot of RFI and probably didn't have much low-level stuff, but now that's not the world we live in anymore. So the real-time cutting and flagging is basically going into the data at its rawest cadence, at its fastest cadence, assessing the RFI on much shorter time scales, removing it before you integrate it, and then hopefully your data is much cleaner. This has been done by primarily LOFAR, which is a radio telescope in the Netherlands, because the Netherlands is where a lot of people are. And so there's a lot of RFI there. There are a lot of radio bands, there's a lot of a lot of communication happening in the Netherlands. So probably the best RFI removal algorithms are coming from that telescope because they just had to deal with it much earlier than most of us did. And so, so there are definitely analysis techniques that we hope can clean the data more efficiently than, for example, what we're doing with CHIME. Certainly, like I said, the next version of CHIME is going to have to build these into the core data acquisition, because we can't live with the current environment. There's no, like, our science is gone right now. So, yeah.
So this came up during the lunch as well, but are there proposals to use AI to help with this data analysis?
Definitely people have, I forgot to say this, definitely people have used AI for trying to find and identify RFI. That's because it's, like I said, the data is kind of Gaussian-ish, but the RFI spikes are these weird transients. And so being able to find either clusters of them or regular cadences of them is one of the ways you can look at from the data. So if you can get the AI algorithms to do that about as well as more traditional kind of standard deviation or whatever cutting, then you win too. Yeah, for sure.
I guess I broadly see these AI algorithms like pattern recognition and generative models, and so you shed some light on the pattern recognition use cases. Are there use cases for generative models, and is it even proper to use generative models for science, where having the model generate new data, like maybe generating it based on what it's already seen, but now you're looking for something that you haven't seen before. So
I'm not sure for RFI. Other people in the audience might be able to think about this more clearly than me. I'm not sure if generative models would be as useful for RFI removal. For sure, for other things like simulating your data more broadly, you might be able to do it more efficiently. Yeah.
Okay. So I guess we move beyond the cosmology aspect, maybe ask you a broader ethical question about the rapid commercialization and occupation of space. And so yeah, is there a concept of a shared commons in space, and do you have any thoughts on that?
Oh my God, I didn't know about this question. No, do you mean like, actually, could you go into more detail?
Yeah, I guess just maybe there's a lot of satellites being launched into space, and there, as far as I know, there isn't a coordination between countries about like where sort of who owns the
Yeah, and where they end up.
who
Yeah,
owns
yeah.
the space
Yeah.
and where they end up and such. And I guess maybe it wasn't a problem in the past when these satellites were sparse.
Yeah.
But now that they're becoming more dense,
Yeah.
perhaps this is something that people are
Yeah,
thinking
yeah.
about.
Yeah, this is a tough one. So I actually don't know that much about it. I will say there are a lot of things in space that other countries don't want countries to know about. So, for example, some of these Russian satellites. There's an optical telescope called the Rubin Observatory that's going to go online next year. It has a huge field of view, so it can see a lot of the sky from an optical telescope, a lot of the sky at a given time. So it sees Starlink satellites go by. It sees tons of these things go. Basically anything that's in its field of view, it's sensitive enough to be able to detect. So it knows about everything that's going to go in front of it, in front of the camera. And so some of those things are Starlink, and the scientists are incredibly worried about this. So this is not the radio bands, this is literally that the Starlink satellites are bright. And so they, if you're trying to make sensitive measurements of this night sky, having these like bright streaks going through your camera really sucks. So they'll definitely know about all the Starlink satellites, but they will also know about all of the satellites that every other country has launched, including the US, and some of those satellites may be satellites the US doesn't want anyone to know about. And so there's a part of their data analysis pipeline, this was at least proposed, but may actually be what they're doing. The images that come off of the camera go to a secondary body that looks through I think it's not the Rubin Observatory, it was a different one that actually had this happen to their data. I think Rubin got a different deal. But this one telescope that could also fly satellites on accident, their data had to go to a separate government body that would look at the images, take out the pixels where there were things they didn't want the scientists to be able to know about or anyone to know about because the images eventually would be public, and then send the image back to the scientists for further analysis. And so, I could imagine that understanding the boundaries and the conditions of where our satellites want to go could be a fraught negotiation, but certainly as more stuff goes up there is the thing you have to do anyway, right? Because otherwise you're going to crash into each other at some point.
Yeah, so I guess another question, slightly off topic, but what role do you think public awareness plays in this whole thing? So do you think if we were to talk about this problem more in like the general public, we talk about satellites for astronomy a little bit more, they could proliferate this concern and it would be a talking point much broader, and how can we get that public awareness?
Yeah. Oh, I don't know how, but yeah, it would be great if the public was more aware. Generally speaking, not if the public cares about science and they care about the science that we do, and they understand that we can help them understand that our science can't happen if Elon Musk keeps sending us satellites that blast things in our bands, then I think you have a case to take that says you should keep this clean, or we need to figure out a better way of doing this, et cetera. I think, like I said, a lot of times we're surprised. We only learn about a frequency band being allocated way after the fact. When we could never have any comment period. In the beginning, Elon Musk's Starlink was better about responding to feedback. So there was an issue where their satellites were kind of bright and in optical, in fact, and they just I think they just coded the satellites and made them dimmer or something. They changed something out in the next generation of satellites that fixed the problem. And it feels like that was a real win for both, great, like everyone got what they wanted. But that feels less possible nowadays, I think. And so, scientists kind of merging and saying, like, okay, please don't you take up our band, can only do so much. We don't have that much leverage if other people aren't behind it. And so, for sure, imagining that this is a resource that we should only give up if we know exactly what we're getting in return and we think that it's worth it, I think is, is important to be talking about and thinking about. Yeah. I don't know how to do it. Like getting the science public interested in science and then getting them interested in RFI of the satellites, like if that's
What is?
But I'd love to do it.
What do you think is the most urgent matter that the public should know about, or urgent concern in your field?
Yeah, I mean, I think probably it's the policy side of it, right? So it's our methods for advocating for what we want don't seem to be working particularly well, or maybe there's a friction between how the scientists can ask for what they want and what comes out of the other side of it. So I think, once you auction a band away and say, you can use it, you're not getting it back, like it's gone. You can't simply turn around and say, stop developing all that technology that you did to put on the satellite, like this is over. So I think that's probably like basically that institutional part is probably the hardest part. But I would say, I personally am most concerned about these cosmic background frequencies because the frequencies we use to see the sky are in bands where we can see through the Earth's own atmosphere. So those are the ones that will be used for satellites also for the same reason, right? Things going up, things going down, it's the same. And so, so I'm most worried about that because I think on the one hand, kind of the radio side, we're starting to try to figure out how to do shared spectrum techniques, things like that. In one way or another, we're going to have to learn how to deal with it because people use, whether it's a satellite or not, people are going to use those parts of the bands. I think the higher frequencies, there's just, right now it's wide open, and so probably people view these as like the goal, just wide open space for them to be able to use all these bands. And I think that would be my most concerning one for sure.
And the last question I had for you was, do you have any advice for younger astronomers? Are there any skills that they should get in future where there are a lot of satellites, there is a lot of interference? Focus
on analysis techniques to remove it from the data because we're definitely going to have to do that. For sure.
Would you recommend for people to have an interdisciplinary background to also maybe advocate on the policy side, also maybe have some science communications a little bit?
That would be, yes, that would be nice. But that's good in general, not just for our bands. But I would say, one thing you could imagine doing, which is one of the things we think about CHIME, is that these communications are known, right? Like it's a specific pattern that you're looking for because they're sending a digital signal down for people to, look at cats on their cell phones or whatever. So, you could imagine a world where you can negotiate a way that you can get that information and remove it directly from your data because you know it's getting transmitted in a non-scary way that's not snooping on people, but just being able to kind of remove that from your data because you know exactly what's getting transmitted. So I think things like that, interdisciplinary is always good, but signal processing skills I think would be like one of the keys for doing this well. But in general we should be better. This may be the lesson of not just the RFI world, but also the last 4 months of government science funding stuff is, we maybe haven't done as good of a job advocating for science and how important it is, and I think we should have been. I think we're reaping that now. So yes, definitely, we should all become effective science communicators, including me.
Well, thank you so much. I spent the last couple of days researching this field that I didn't know too much about. And learned, but then I still learned a lot more during this conversation. I hope everyone else did as well. And so yeah, that wraps up all the questions I had. Thank you so much for your time.
Great questions.
And so we'll open it up to the audience. We have about 15 minutes or so to take questions from the audience. So yeah.
There was a recent law that was passed that said that American scientists are no longer allowed to share genetic information with Chinese scientists. So there's a number of Alzheimer's databases and things like this that are now closed.
Yeah.
And it's led to a lack of collaboration, and shutdown of collaboration between U.S. and China labs that were previously doing basic science together for health, not like real science.
Not evil things,
And I'm wondering, do you have concerns about that with space, given that it's becoming increasingly a military domain? And where do you see the future of collaboration heading?
Yeah, so I'll say certainly with China, it's already a problem. So when I get an MSF for a NASA in particular, I'm like required to say that I will share no technology at all with China or whatever. There's a list of countries, you can imagine what they are, but I'm not allowed to share anything with them. It impacts, and it's getting worse now, but it impacts graduate students. So it also means frequently you can't take on graduate students from again, unnamed countries, but you can imagine what they are, whatever. Because they're not allowed to handle material. I'm sure this is true for data, but they can't handle technologies and things like that may be sensitive one way or another. And so it's like that part is tough because there are a lot of really good students in China and work to have them as graduate students and work with them. Traveling to China is complicated, so it's it's only going to get worse, but maybe eventually it'll get better. So, like I would say, already even without these laws, it's already been complicated at some points to be able to collaborate broadly. That hasn't really been a problem with European, et cetera, collaborations, but certainly with China, that's not good. Let's see. It's also, China is increasingly a bigger player in science and in funding science, fundamental science is happening. And so it reduces the amount of collaboration that you can have with them as well. So if they build, they built a radio telescope called FAST. It's the biggest radio telescope in the entire world. They evacuated an entire village of people so they could take over this valley and put a huge telescope in it, basically like Arecibo but bigger. And none of us will ever get to use any of that data. There's no way to collaborate on it. So certainly politics impact the collaborations you can do, and that does have a chilling effect on science for sure. Yeah. And it will get worse as China is a bigger and bigger player in fundamental science.
I wanted to ask more about the process you described of governments auctioning off parts of the spectrum. Like, do I understand correctly that for Starlink to start using some part of the spectrum, they do have to go through some process with, is it just the US, is it several governments? Who are they actually meeting with? It sounds like there is a moment in their beforehand where they could, governments could be asking for comment from scientists that aren't. So I just want to understand better what is happening.
I don't know. So this process is also opaque to me, which I wish I understood it better. The FCC is the one that's, when Elon Musk says I want the 30 to 30.1 gigahertz band, the FCC says pay me $1 billion and you can have it. The FCC is the one actually controlling that. How that happens, how that gets communicated and discussed internationally, I don't know. So, I don't know if there's also a notice that goes out that says, hey, everyone, we're letting Starlink have this band, or if there's a, process of, you know, a 60-day comment window or something from other countries, I'm not sure. I think the FCC, so probably, so I'm not sure, but the various spectrum management and sort of national academies, this core committee, et cetera, I think broadly what they do is say these science cases are interesting. Please try not to take these chunks of the band if you can. And so the SEC either takes that or doesn't, depending on how much they care. But yeah, I'm actually, the process is quite opaque to me. It does feel like I kind of learn about these things only when someone says, hey, by the way, this might be showing up in your data pretty soon. I'm like, what? So it's opaque to me, and I should certainly understand it better. But you know.
I know you said not everything can go into space, but from an optimistic perspective, are you excited about some of the telescopes we can design for Starship and its increased payload size? So things don't have to necessarily fill up as much as the James space telescope.
Yeah. So I think like we should still definitely do science in space. So the fact that NASA's budget may be cut by 50%, mainly for science, that's bad. So we should keep putting telescopes in space. The James Webb Telescope launched a year ago, a while ago, over that. And that is an example of a telescope that could only exist in space. So, you know, the Hubble is a great example of that, also from a making science accessible to regular people. It's incredibly successful in addition to being a very, very fruitful scientific camera. X-ray, like I said, X-ray satellites can only go in space. I think the ambition for what we can put in space will get bigger, but as that happens, it will also get more expensive. So likely we'll start seeing like CubeSat still continuing to happen, so things on very small scales and things on bigger scales, but it's probably going to be harder to do stuff in the middle. And even then, any given space telescope takes decades to come together. So unlike on the ground where you can build things more quickly, you know, you start the planning process, and then like 30 years later, something might get launched and you see the benefits of it. So, you know, there's a trade-off there of science and time as well. So I think, you know, I usually try to, when I'm thinking about what's useful to put in space, not that I make these decisions, the things that can only happen in space and could never happen on the ground is how I would make that decision, because it is much more expensive to put together in space. Prohibitively so, or, you know, put things out in space. So I think, you know, we should be really ambitious, and we should be imagining what the future telescopes could look like as payloads get bigger and all of that. But I think we should also keep in mind that that's never going to be the only way that we do science.
Yeah.
Yeah, just a quick question on a point about public awareness or lack of public awareness around this issue. I guess I'm curious as to how much you think that might be because of the general public understanding that a lot of science is apolitical, or that there isn't a lot of politics associated with sciences, specifically astronomy, and how that actually hinders public awareness or advocacy on part of scientists with the public and getting them more involved with or aware of issues like this and others.
Yeah, I think astronomy is an interesting one because generally speaking, unlike some branches of science, it is pretty uncontroversial, right? So people like love looking at pretty pictures of the universe. Like my mom will frequently ask me about something she read, like that I know nothing about. She's like, did you know that this planet was just found around this star and it's something? Oh, great. So like I think astronomy is one of these, like, because it's so uncontroversial, it's one of the places that you get a little bit of a like leg in the door for being able to say, doing science like this is important. And if you want to keep it going, here's one way you can help. Advocate for clear, dark skies and dark radio skies too. So I think like there is an opportunity there as well, but but it is it's a long thread to go from like, do you like these images? You should call your congressperson and tell them that stay away from the 40 gigahertz band at the spectrum. So yeah, so figuring out how to effectively do that is incredibly worthwhile. And astronomy might be one of the ways that you can kind of get that. I say that, but obviously a bunch of astronomy funding is on the line right now. So, we'll see how much people really care. I could be wrong.
Thoughts on that?
Yes, thank you. Laura, is it possible to argue that astronomy scientists in, say, China are getting ahead and doing much better than scientists here in the United States? Because they don't have the same restrictions or they have better access to spectrum. Is it possible to argue this straight? One could say, well, listen, they're getting ahead, so
Yeah.
that's one argument.
Yeah. Yeah, I mean, I think, so China's really excellent at, so this is, whatever, next 5 years, all this is gonna change. But China is really excellent at building stuff, but so far has been less effective at getting useful science out of it. That's just a statement of where they are in the process of going from, of competing with the US and then catching up finally. Like it's not, that's, again, in 5 years, all of that, everything I just said could be wrong. So, they are really effective at building the infrastructure that they need, like this fast telescope that's bigger than Arecibo. They built it in some insane amount of time, like a year or so. Like, I can't imagine anyone building anything faster than that. The instrumentation that they put on it was still not competitive with what we're usually putting together across the US and Europe. So, like I said, that's a statement of now, not a statement of 5 years from now. There's no reason anyone wouldn't catch up with that. There's no technical reason why that's true. It's just you have to learn how to build it and then do better, right? So I think right now we're not quite at the stage where you can say China would be better than us. But in 5 years, I'm not sure that I would be saying the same thing. For the spectrum management, certainly, if they decided that, from what I know of their governance structure, if they decided that some bands should be clean because it's important for their science cases, I think they would be much better at making sure they stay clean than we would be here in the US, for sure. So, if there's a science case that turns out to hinge on some frequency band that we auctioned away and they didn't, they'll be the only ones that can do it.
Questions? More questions? Yes.
I guess conversely to that, does working with other countries that were not out of territory, who have that frequency band building, is that something that I don't know the scientific community is looking to?
Yeah, I mean, so the other telescopes I work on, for example, to get away, so one way we could try to deal with RFI is to make better algorithms for removing it. The other way is to go to places that are already clean. So basically where there are no people. So one of them is a telescope I'm working on in South Africa. That's one of the places you can go. There's a desert there, no one lives there. So there's you don't have any of these RFI problems. Canada used to be like that. Australia, the middle of Australia, another place like that. Northern Canada is still true, so you could go to Northern Canada. So there are places on the Earth where if you are interested in a particular band, you can usually find it in the region, or even, shockingly, a few places in the US like that. But it does require international collaboration, right? So the US has to be willing to collaborate with Canada, which until recently I could have said was trivial, but maybe now not so much. You do have to be willing to collaborate with South Africa, with Australia, yeah. So there are places where collaboration can certainly get you out of some of these holes. Yeah.
And are there any other geographical restrictions besides under the frequency band? Does like altitude matter?
Yeah, for radio frequencies, it doesn't. For the CMB, these cosmic microwave background frequencies that are much higher, those you can only do in places that are very dry. So that's why the telescopes are in Chile and not the US. The other classic place to build them is Antarctica. So usually we're like very restricted to being able to go to places like that. For the radio telescopes, you're mainly looking at areas where there are just no people and you don't have a lot of other things going on. I'm trying to think if there's any other, you don't want to build in sensitive areas like either for, ecological reasons or like human inhabitants reasons or whatever, like, you want to be sensitive about things like that, but otherwise, yeah, there's no, for the lower frequency bands, there's no real, put it anywhere.
No, it's going back.
With all these new advancements in the potential militarization of space, do you think there is need for a new governing space treaty or some amendment to the OST? Or
I don't know what the OST is.
outer space treaty?
Having any form of governance over space sounds really great. I would love it if we had less of this junk and more communication about what ends up there and things like that. Yeah, definitely.
Actually, this is something that we didn't get a chance to talk about, but the space junk
Yeah.
affects astronomy observations.
Not yet, but so sometimes you can see some things go by. So in a few ways like that, Starlink and things like that are worse for reading the space junk. More it's the broader thing of it makes it harder to start. It's harder to launch things, and more of it, as more and more of it accumulates, that space is no longer clear, and so you can't just put things there. For sure, things like Hubble get dinged a lot. So if you were putting anything in your Earth orbit, that's that can get tough if you wanted to put a really sensitive telescope out there. Yeah. I'm not sure.
I have a quick question. So your CHIME data,
Yeah.
is that public?
No, our CHIME data is not public yet. Probably someday we'll make it public.
Out of curiosity, what is keeping you guys from making it public?
We're a very small collaboration, so we don't have a lot of time to do things, so that's one. The other thing is that it's actually massive, so the place where we analyze the data is Canada's largest computing cluster. So it's not like we can just put all of the time streams, like our full 5 years of data, on like a disk and hand it to someone or whatever. Like it's, we take up, I'm actually not sure what our current data volume is, but it's quite a lot. So the thing we'd release would be the maps, for example. So we'd make a map of the sky and be like, here's a map of the sky from the CHIME telescope. So we haven't gotten to the point of releasing stuff like that. Definitely it's in one of the grants that we got does require some of our data to be public. So eventually for sure will be. It's not out of malice, it's out of laziness, I guess, or lack of time, plus no interest in maps yet.
Okay, I'm curious on you here that if you have a lot of this data that is public, maybe not easily accessible, but not constrained in some way, in the way that some other telescopes are, right? If you have these transmissions from like you said, the Russian satellite, where it's straight into your face, right?
Yeah.
There's still a Fourier transform to take out that frequency, but I see and I can tell that there's
Yep.
Russian satellite. That's great.
Well, you know us now. You have to go figure out where it's coming from. So, yeah.
Actually, a follow-up to that point. So we were talking earlier, and you said that there's government bodies that censor some of your data, and they take out some pixels or ten slices.
Yeah.
Do you think it's going to get worse if there is a space governing body that there's more red tape there, and there's more people who want things removed?
Could be. So that, I think Ruben managed to get out of this. So the bigger telescope collaboration kind of ixnayed this concept, which is good. So I forget which telescope it was that got impacted by this. It is possible that when you have more formal governance, you also come with more requirements. Could be less, right? It could just be like, well, we already let them, so who cares,
We'll maybe take the last question.
Dual-use technology is very complex, but it also provides an additional sources potentially for funding and for interest. And so I'm wondering, like, do you think that if these telescopes are powerful enough to detect these satellites and potentially be useful for intelligence operations in addition to their scientific missions, that you can get funding for them from a defense source, especially as NASA and alternatives as funding is
Certainly that has crossed many people's minds, and I believe at least a few proposals along those lines have done it. Yeah.
at least for AI, this is for national security purposes, and we need to beat China,
Yeah.
and those two arguments are really effective.
Yeah. Good to know.
Okay, so that wraps up our discussion. Let's thank so unfortunately, we don't have any more time for small group discussion questions. We will maybe just put them up just in case if people want to talk informally. But yeah, we'll end these end here. Thank you so much for coming. Please sign up for the mailing list and have a lot more events. As Mason said earlier, we do a lot of science plus policy type events. So I hope we can attend future events. Thank you so much for coming.